In the previous class, we started talking about response of first order RL circuit. We didn't talk about RC circuit. And probably today also we will not have time to talk about RC circuit. So what I said in the previous class, I told you that I have two different types of response we are going to study in that course. The first one is called natural response, and this is what we are studying right now. I'm charging the inductor or the capacitor, then I'm removing the battery, and the capacitor or the inductor is leading the circuit by itself without any help from any other source. This is what we are meaning by natural response. And also I told you that we have forced response, and forced response means the capacitor is leading or is feeding the circuit, but with the help of another source, voltage source or current source, and the same for the inductor. So we didn't start talking about step response or forced response yet, but in the previous class I started talking with you about RL circuit in case of natural response. I'm charging L and then I'm disconnecting the battery or I'm disconnecting the voltage source, and the inductor itself is feeding the circuit, or in other words, is discharging. It's a charge in the circuit. And I showed you that circuit, and I told you that if I have something like that, and I have current source here, and I am expecting based on that current source that if the switch is closed, this current will go directly to L and the circuit will look like that. Why? Because this is DC. So the inductor will be charged to a certain value. After that, if I opened that switch, at that time I'll have that circuit. And I have RL circuit and I have the other parts of the circuit, but actually there is no current here. That's why I told you I would like to talk about this circuit only. I'm not looking for that circuit because I will disconnect it. Now I would like to see the behavior of the current inside the inductor in case of RL circuit. So I have initial charge here, which is equal to IL of 0. Then I try to find the relation between the voltage and the current by using the equations that we learned before. And we said that summation the voltage is equal to 0 for that loop. And we said the voltage across the inductor is equal to LdI by dt, and the voltage across the resistor is equal to R multiplied by I. Based on that, I wrote these two different terms. And I told you that this is first order differential equation. We studied in mathematics how to solve that equation for finding I. We learned in mathematics, if you would like to calculate I, what you have to do, you will use separable method, which means you will separate everything related to I in one side and everything related to the time in the other side. And this is what I did here. And I found that di over I is equal to negative R over L dt. And then, based on what we learned in mathematics, we said we will take the integral for both sides. If you try to take the integral for both sides, the integral for the left-hand side will be from I L of t0 to I L of t. And the integral for the right-hand side will be from t0 up to t. And based on that, we derived the equation for the current IL of t, and we said IL of t is equal to IL of t0 multiplied by e to the power negative R over L multiplied by t minus t0, whereas t0 is the time 0, or in other words, the starting time. And for simplicity, we said if t0 is equal to 0, at that time, I can substitute this guy by 0, and I can substitute t0 here by 0, and at that time, I can write IL of t equals IL of 0, which is the initial stored current or the initial current in the inductor, multiplied by e to the power negative r over L times t. And based on that, we tried to draw the relation between the current and the time. And we found that if the inductor is connected in series with the resistor, the inductor will try to discharge its charge or will feed the resistor. At that time, the current value will be reduced because the inductor looks like a storage battery, like what you are using in your cell phone, a storage battery, and it is feeding the circuit that's connected to. That's why the current is trying to be reduced gradually. At a certain time, the current will be equal to 0. And we didn't calculate the voltage, we didn't calculate the power, we didn't calculate the energy. If you still remember from the previous class, I told you I have 4 different components. I have to know them. I have to know the current, the voltage, the power, and the energy. So right now, I will try to find the equation for the voltage, the equation for the power, and the equation for the energy. But before I start talking about those equations, I mentioned in the previous class that the current, in case of the inductor, is not changing instantaneously. Which means what? It means if you are talking about the current in this guy, immediately before moving the switch, imagine immediately before moving the switch, the current was IL of 0 negative. Because I'm assuming T is equal to 0 at the time at which I open the switch or I move the switch position. So imagine I have T0 negative and T0 positive. T0 negative means what? Means immediately before moving the switch position or opening the switch. So immediately before opening the switch, what is the current here? It was equal to the current IS. Immediately after opening the switch, I'm going to call this current as IL of 0 positive. So I have 0 negative immediately before and 0 positive immediately after. So immediately after moving the switch, what is the current in this circuit? It's still IS. This is what I mean by the current is not changing immediately. But if you try to look to the voltage across this guy right now, it is equal to I times R. Am I right? But before opening the switch, the voltage across this guy was equal to what? 0. So the voltage across the inductor is changing immediately. Pay your attention. We have voltage at T is equal to 0 negative, it was 0. And immediately after moving the switch, the voltage became another value. But for the current, no. The current in case of the inductor is not changing immediately. And this is what I wrote here. I wrote here the equation for I, and I wrote that the current in the coil is not changing instantaneously. Which means I of 0 negative, I mean IL of 0 negative, is equal to IL of 0 positive is equal to IL. IL of 0 negative is equal to IL of 0 positive is equal to IL of 0. This is the current at 0 time. But what about the voltage? No, it is a different story. I'll try to find the voltage right now. So IL of 0 negative, it is the current immediately before opening the switch. And IL of 0 positive, it is immediately the current immediately after opening the switch. So this guy before opening the switch and this guy after opening the switch, and both of them are equal. That's why for most of the cases, in case of RL, I'm going to ask you to calculate IL of T for T greater than or equal to 0. But in case of the voltage, no, I'm going to say calculate the voltage in case of T greater than or equal to 0 positive. Why for the voltage I'm saying that? Because for 0 negative, the voltage was equal to 0. But for zero positive, I have a value of the voltage. But for the current, no, zero positive current is equal to zero negative current. Any question, guys? Now, let us talk about the voltage. If I would like to calculate the voltage across this guy is equal to LdI by dt. Am I right? The voltage across the inductor, it is equal to what? LdI by dt. So if you would like to find the voltage across the inductor, you have to find the first derivative of this guy with respect to the t, which is the time, multiplied by L, because the voltage is equal to LdI by dt. But at the same time, I can say the voltage across the resistor is the same like the voltage across the inductor. Am I right? I have the same voltage, so this voltage is equal to this voltage, maybe opposite direction, because when I added them, I said the voltage across L plus the voltage across R. So I can say right now, the voltage between these 2 points is equal to I multiplied by R. But pay your attention, this voltage that you are calculating is the voltage across the resistor. It is not the voltage across the inductor. It is the same, but different direction or opposite polarity. Are you seeing what I'm talking about, guys? So if you try to talk about the voltage, I will clarify that again while I'm talking about the energy. If you try to calculate the voltage between these 2 points, for example, I'm going to call it V of t. So V of t, based on that equation, V of t should be equal to I of t multiplied by R, which is equal to, from that equation, I can say it is equal to what? I can say it is equal to I of 0 multiplied by R multiplied by e to the power negative R over LT. This is in case of t greater than or equal to 0 positive or 0 negative, or generally speaking, 0. For the current here, I can say this is in case of t greater than or equal to 0. Am I right? I can put it 0 positive, I can put it 0 negative, and I can leave it 0, because the current is the same in all cases. But what about the voltage? This voltage in case of t greater than or equal to which 0? Positive or negative, or generally speaking 0? I think positive, because before moving the switch, which was 0 negative, the voltage was equal to 0. Now, if I would like to find the current, the power, I can say the power P of t is equal to V multiplied by I. V of t multiplied by I of t, right? Or I can say this power is equal to I squared multiplied by R. Or I can say this guy is equal to V squared divided by R. This is the power. So if you would like to find the power is equal to I squared multiplied by R, or V squared divided by R, or V times I. So I can say this power should be equal to I of t squared multiplied by R, which is equal to I of 0, IL of 0 squared multiplied by R multiplied by e to the power negative 2R over LT. Because I squared of this guy will be IO squared times e to the power negative 2, because e times e will be e to the power 2. That's why I wrote here the power is equal to IL of 0 squared times R times e to the power negative R over L times T. What about the energy? If you would like to calculate the energy, W, the energy is equal to integral for P of t dt. This is from 0 up to t. If you try to find the integral of this guy, which is the integral from 0 to t for this term, which is I L of 0 squared times r times e to the power negative 2 over r, sorry, 2r over L t dt. So if you try to find the integral of this guy and substitute by the limits of integration, you will realize that the energy will be equal to half L I O squared multiplied by 1 minus e to the power negative 2r over LT. This is in case of t greater than or equal to 0. Now, my question is, if you try to look to the energy equation is equal to half Li squared multiplied by 1 minus e to the power negative r over Lt, right? At t is equal to infinity, this term will be equal to what? This term will be equal to 0. If this term is equal to 0, so the energy at infinity is equal to what? Half L-I-O squared. Is this logic? I'm expecting after time, the coil will do what? Excuse me? Yes, will run out of energy. But you are telling me based on that equation, after a specific time, which is I don't know, based on the equation, it is infinity, but it is a specific time, I know, based on the charge. So after a specific time, the energy will be equal to half L-I-O squared, which is similar to the initial energy. Half L-I squared, because I know the energy is half L-I squared, right? And you substituted by I L of 0, which is the initial current. So how come I'm seeing here the energy is equal to half Li squared at infinity? And my friend is saying, oh, it will run out of energy. I don't know. What's your opinion, guys? But here the equation is giving me a certain value. This is at infinity. The switch is already moved. It's not logic. But the equation is giving me the initial energy. What happened? Excuse me? Yeah, but the energy I'm expecting, the energy across the inductor should be equal to, I'm expecting that energy should be equal to, I'm expecting by the time it will be 0. Did I make any mistake? The first thing you are going to say, oh, you did a mistake. No, I didn't make any mistake. But what happened? Yes. But I'm calculating the energy.
But at t is 0.
This is the energy at any time t. If you substitute it by t is equal to 0, it gives you 0 energy. If you put here t is equal to 0, this term will be 1 minus 1 will be. So at t is equal to 0, I got 0 energy, but at infinity, I got the whole energy. So this is opposite to what I understood. Why? Because from the beginning, if you still remember, I told you I'm calculating the voltage across the resistor. So this equation is giving me the energy given to the resistor. At t is equal to 0, there was nothing here across this guy. This is logic. But at t is equal to infinity, yes, I don't have anything here. And everything is discharged and given to the resistor. That's why I am expecting that equation. If you still remember, I told you at the beginning, I'm using the equation of the voltage across R. So I'm expecting this guy is related to R. But what about if you would like to find W for the inductor? What you have to do, you will go back to this equation and try to find its voltage, which is LdI by dt, and then try to find the power, which is equal to VI, and then try to find the integral of that guy. At that time, you will get something opposite to this one. But based on that, I can calculate the initial energy stored and the final energy, but in opposite way. So the initial energy stored, if t is equal to 0. And the final energy, if t is equal to the initial energy stored, if t is equal to 0. The initial energy stored. And the final energy at t is equal to infinity, sorry, the initial energy stored at t is equal to infinity. And the final energy at t is equal to 0. Are you seeing what I'm talking about, guys? Because here I'm talking about this guy, but based on the calculated voltage across the resistor. Okay, guys? You got that? Any question? You have to use this equation for finding the voltage. It should be. And from the beginning, I told you that voltage is equal to that voltage as a magnitude, but with opposite polarity, right? You have a question? Okay. Any question, guys? Okay. Let us continue talking about that story, but right now I would like to rewrite all of these equations in a more nice format by using something called tau. What's tau? Tau is defined as time constant. And this tau is equal to L over R. And this time constant is defined as the rate at which the current or the voltage approaches 0. So I'm going to go back to all of these equations and I'm going to substitute each L over R by this new variable, which is called time constant, which is the rate at which the current or the voltage approaches 0. So I'm going to use this equation for the power, but after substituting L over R by tau. So this equation will be written as e to the power negative 2t over tau. And this guy will be written as e to the power negative 2t over tau. And this guy will be written as e to the power negative t over tau. And this current should be written as e to the power negative t over tau. So if you try to rewrite all of these equations again, you will realize that I of t is equal to I L of 0 multiplied by e to the power negative t over tau, where is tau? L over R, which is the rate, which is considered at the time constant, the rate at which the current or the voltage approaches 0. And V of t should be equal to I L of 0 multiplied by R times e to the power negative t over tau. And by the same way, I can write B of t, which is equal to I L of 0 squared multiplied by R times e to the power negative 2t over tau. And I can write as well the energy W of t, which is equal to half L I L of 0 squared multiplied by 1 minus e to the power negative 2t over tau. And there is no need every time to mention that this guy for t greater than or equal to a0, and this guy for t greater than or equal to 0 positive. No need to mention that, and by the same way, I can find P and I can find the energy. Let us see problem which is talking about that story. So I would like to copy problem from the notes. I'd like to rewrite it. So I think note 6. Let me copy this problem. And paste it here and try to solve it. So for this problem, he gave me the following circuit, and he asked me about what? So for this circuit, he said the switch in the circuit has been closed for a long time before it's opened at t is equal to 0. Find, and this is the circuit. So the switch was closed and then it is opened at t is equal to 0. He said, for this circuit, can you please find IL of t for t greater than or equal to 0? I0 of t, actually it's not I0, IO of t, where is IL of t? Actually IL of t, which is the current in this guy. And IO of t for t greater than or equal to 0 positive, you would like to find this current at any time. And V0, actually it is not 0, it is V out, VO of t for t greater than or equal to 0 plus, and then the percentage of the total energy stored in 2 Henry to that dissipated in 10 ohms. Let us first calculate the current and calculate the voltage, and then we will talk about the energy. But before we start solving this problem, what we have already derived, we derived some equations based on a specific circuit. What is this circuit? It is R connected in series with L. Again, I derived all of these equations based on one R and one L. Am I right? What about if I have 10 R connected parallel series and many L connected parallel series? Can I use these equations? The answer is you have first to find L total and R total. And then you can apply these equations. But you couldn't apply these equations for the circuit if you have many R and many L. You have to find the equivalent R and the equivalent L. Or convert your circuit to be similar to this one. At that time, I can use or apply these equations. Before that, I couldn't. Let us see this problem again. Here, he told me that this switch was closed for a long time, and then it is opened at a specific time. What's needed? He would like to calculate the voltage, the current, and the energy. But if you try to look to the circuit, you have R, you have R, and you have current source. So the first step for solving the problem is to find the initial current in the inductor. I'm happy because I have only one inductor. I will not find L total. But the problem is I have more than one R. So I have to find R total after opening the switch. Let us first see before opening the switch. So I have to find IL of 0 before opening the switch, right? So I will copy this circuit and then I'll put it here. And I will try to see how to deal with this circuit. So the circuit was looking like this one. Before opening the switch, this guy was closed. So if you try to look to the circuit, I have 20 ampere solution before moving the switch. Before moving the switch, this guy is closed. So this guy looks like what? The inductor, sorry, looks like a short circuit. So this guy looks like a short circuit. This is before moving the switch. So I have this current. This current is trying to flow in that way. This is 20 amps. And here the current will be distributed. Am I right? Oh, we have this guy short circuit. Just 1 second. You have first to find the equivalent of those. So the equivalent of those will be something like that. Right? Then this current will go in that direction. This guy in parallel with this guy, in parallel with this guy. So based on that, what's going to happen, this current will go in that direction. So what is the initial current? IL of 0. It's equal to 20 amps. So I can say based on that, IL of 0, negative or positive? Actually, I'm calculating negative right now, but it is positive as well. So I will write it IL of 0, generally speaking. So IL of 0 should be equal to, based on that, 20 amps. But just 1 second, what's going to happen if I have a resistor here? If you have a resistor here, the story will be different. So I have a current here that will go in that direction, right? And the current here will try to look to this and this. So which branch the current will prefer? The current will prefer to go in this guy. But if you have a resistor here, I will draw that resistor here. At that time, this guy is considered as a short circuit. For what? For this branch only. After removing this branch, what's going to happen? I have this short circuit connected in series with this resistor. Am I right? And after that, the current will be distributed between this branch and this branch. Do you like me to repeat that? Again, what about if I have different configuration? If I have another problem that has resistor here. If I have a resistor here, what's going to happen? This current will not go directly to this guy. Why? Because this short circuit is short circuit across this one only. And based on that, I can redraw my circuit again that will be something like that. This is in case of I have a resistor in this guy. Are you seeing what I'm talking about? This is not the scenario for that problem, but I'm imagining if I have a resistor connected here. At that time, this resistor is this. At that time, this guy is short circuit. The current here will be distributed between this guy and this guy based on the current divider identity. I have to pay your attention to that. This is one of the tricks I'm using in the final exam. Okay? Any question? Now, let us continue solving this problem. I have already found what I'm looking for, which is IL of 0. The next step is I will redraw the circuit after opening the switch. So after opening the switch, or moving the switch, what's going to happen? I will have this circuit. This guy is 2 ohms. This guy is 10 ohms. This guy is 40 ohms. This is IO, and this is VO that you are looking for. And the current here is IL. Oh, sorry, this is not IL. This is R. So the current here is IL that he is looking for. And I have initial current here. Let me change the color. So the initial current here, IL of 0, is equal to 20 amps. This is IL of T, and this guy IO of T, and this guy is VO of T that he is looking for. What about this circuit? This part, I still have it. Am I right? I still have this circuit, but this switch is open. So you can draw this circuit here by opening the switch. So right now, there is no relation between this circuit and this circuit. That's why I ignored it, because I didn't ask you about that circuit at all. I'm asking you about the coil. So what is the next step? The next step is to calculate IL of T. How to calculate IL of T? This is the equation for IL of T. I have to find tau, which is equal to L over R. But which R? R total. Because all of my equations that I have already derived, based on having only one resistor and one inductor. So I will try to find R total. So R total here, these two are connected in parallel. The overall is connected in series with 2. So the first step for solving such a problem after opening the switch is to calculate R equivalent, which is 10 parallel with 40 plus 2. This guy, if you try to calculate it, it is equal to 10 ohms. So based on that, I can redraw my circuit to be like that. This guy is R equivalent, and this guy is IL of T. And what is the inductance? It is 2 Henry. This guy is 2 Henry. Now, am I allowed to use IL of T equation? Yes, you are allowed, because you have only one R and one L. So at that time, you have to calculate tau, which is equal to L equivalent over R equivalent, which is equal to L2 divided by 10. This guy will be equal to 0.2 seconds, because it's time constant, right? Now, if you would like to find IL of T, it is equal to IL of 0 multiplied by e to the power negative t over tau. So this guy will be equal to which I have it, which is 20 over there. So it's equal to 20 multiplied by e to the power negative t over tau. This guy could be written as 20 times e to the power negative 5t, because 1 over 0.2 is 5. This is my current in amps. This is in case of t greater than or equal to 0, positive or negative? Any 0, because this is I, it's not voltage. So it doesn't matter if it is 0 or positive or 0 negative, or generally speaking 0. Because the current is not changing instantaneously in case of the inductor. Now, the next step is, this is the first part he asked you about to calculate IL of T. Then he asked you to calculate IO and to calculate VO. How to calculate IO, guys, in this circuit? Excuse me? How to calculate VO? Should I use the equation? Yes. No, I shouldn't use the equation, because if you try to calculate V, it will give you this V from the equation. But I don't need this V, I need this V. Am I right? So if you calculated V from the equation, it will give you this V. But I didn't ask you about V across the inductor. I asked you about V across 40 ohms, not across R total. So what should I do? Current divider. Yes, I'm going to use the current divider. You scared me. I'm going to use the current divider. I here, because I have this guy is connected in parallel with this guy, so I can use the current divider. Since I know this guy, I can find this current. So this current is equal to this current multiplied by this resistor divided by the summation of this and this. But my question right now, what about the sign for I? Is it the same like IL, or it is an opposite direction? It is so its sign should be negative. So if you would like to use the current divider and you would like to find this current, you have to say negative IL multiplied by this resistor divided by the summation of 10 and 40. Back rows, are you seeing what I'm talking about, guys? Any question? So let me go back to calculate IL using the current divider, identity. Then I can say that I O of t is equal to negative IL of t multiplied by 10 divided by 10 plus 40. If you try to calculate this guy, it's equal to negative 4 times e to the power negative 5t amps in case of t greater than or equal to 0. Positive or negative or any 0. It's positive because this is after moving the switch. So this is 0 positive. Now he asked me to calculate VO. VO is equal to 40 times IO. It's straightforward. So if you would like to calculate VO, I can say VO of T is equal to 40 multiplied by IO of T, and this guy will be equal to negative 160 times e to the power negative 5t in case of t greater than or equal to 0. Positive as well, because before that, the voltage was equal to 0. Then he asked you to find the power across 10 ohms because he would like to find the energy for 10 ohm resistor and the energy for the coil and find the percentage between them. So if you would like to find the power in 10 ohms, how to find the power? I have to find the current here first, right? Or I can say the power for this guy is VO squared divided by 10. So if you would like to find the power for 10 ohms, it is equal to VO squared divided by 10, which is equal to 2560 multiplied by e to the power negative 10t in case of t greater than or equal to 0 positive. And based on that, I can find the energy in 10 ohms, which is equal to integral from 0 to infinity for this guy, which is 2560 e to the power negative 10t dt. This guy will be equal to 2560 divided by the integral will be divided by negative 10, yes, multiplied by e to the power negative 10t. This is from 0 up to infinity. So if you try to calculate this guy, it will be equal to 256 joules. Then he asked you to calculate the energy at infinity for the inductor. Or I can say the energy is equal to half LIO squared, right? The energy, let me go back to this one. Maybe you are not seeing that. Here. He would like to find the energy across the inductor, the initial energy. Should I put T here is equal to 0? The initial energy for the inductor. Should I put T is equal to 0? If I put T is equal to 0, it gives me 0, because e to the power 0 will be 1, and 1 minus 1 will be 0. So it is not, for this guy is not representing the energy for the inductor. You can use it, but you have to put T tends to infinity. At that time, the initial energy stored, which is the energy that's why I didn't write subscript L here. The energy stored in the inductor should be equal to half Li squared. Am I right? So the initial energy for the inductor at 0 time is equal to half Li squared. Again, I didn't put in this equation T is equal to 0. Okay, guys, back rows. I didn't put here T is equal to 0. Because this guy is representing the energy for the inductor if you use the opposite time. Like, for example, if I would like to find the initial energy, I have to put T is equal to infinity. Because this is representing the resistor. It's based on the voltage across the resistor. So based on that, I can find the initial energy stored, which is equal to, if you try to calculate it, half L, which is equal to 2 multiplied by I squared, which will be 400. So initial current, because it was 20 square will be 400. This guy will be equal to 400 G. And if you would like to find the percentage of the energy in case of 10 ohm and the energy in case of the inductor, you can divide those, which is this guy 256 divided by 400. And this is what he asked me about, which is 64%. So what I need from you today is to know how to use the equations for the inductor. If I have RL circuit, how to use the equations for the inductor for finding the voltage, for finding the current, for finding the power, for finding the energy. I have to put in your mind, I couldn't use these equations unless I have only one R and one L. So if I have many R and many L, I have to find R equivalent and I have to find L equivalent. And after that, I can distribute the current or the voltage and I can calculate the power. I think that's enough for today, but if you have any question, please stay. I will stop recording. Then the second midterm will be on Friday, and we will start at 10:30. Okay? Wish you all the best.